Okay, so let's discuss another dynamic programming problem, namely the longest common subsequence problem. So, the longest common subsequence between two strings x and y is the length of the longest common subsequence contained in both those strings. So, for instance, both these strings ABAZDC and BACBAD both have the substring, let's call it BC, right? BC, right? But they also have longer substrings such as BAD, BA, BAD, and the longest common substring would be ABAD, ABAD of size 4. Okay, so pretty simple. Um, pretty simple. Now, the problem is we need to derive a dynamic programming algorithm that finds the length of the longest common substring. So the question is, how do we do that? How do we plan out the recursion? So we start off like we did before. We have two strings, and we order them so that, at every turn, we order them. The two strings are arrays, right? So we say, okay, like we did with the edit distance problem, we're going to consider the strings and we're going to make recursive calls to our algorithms using the prefixes of those strings, right? So we define the two strings A from 1 to M and B from 1 to N, and reason that if AM is not equal to BN, then what does this mean? Then it means that the ends here, that these characters cannot both be part of the longest common substring, right? The longest common substring, because they're common, it only comes about when both characters at the end are equal. So if these characters are not equal, either the last character of A is not part of the longest common substring, or the last character of B is not part of the longest common substring. Okay? Next, what if the two characters are equal? Then we have a choice to make. If the two characters are equal, it's possible that they're both part of the longest common substring. Okay, in which case the longest common substring would simply be 1, i.e. the two equal characters, plus the longest common substring of the prefixes of both strings. Or AM and BN are not part of the longest common substring. In that case, we do the same thing as we did here. We basically either assume that the last character of A is not part of the longest common substring, or the last character of B is not part of the longest common substring. And what should our base case be here? Well, our base case here should be, what was it in edit distance? What was it when we were calculating edit distance? Well, if either of the strings have no more characters, then our base case is 0, right? If our base case is, if either of the strings have no characters, there's no more characters you could add to the longest common substring. So we just say if I is equal to 0 or j is equal to 0. Okay, so our total recurrence relationship becomes like so. The longest common substring of two prefixes of the prefixes of A and B is equal to, if the last characters of those prefixes are not equal, then either one of those characters is not part of the longest common substring, and then we recurse on itself. Or if the two characters are equal, either those characters are part of the longest common substring or they're not. Simple as that. So we have a good recurrence relationship, and we got it pretty fast, mostly because we already did a similar problem in the edit distance problem. So what's the running time of this problem? The running time, well, how many inputs are there? How many subproblems are there in LCS? Well, I I could be one, can be one of n prefixes of A. And similarly, J can be one of n prefixes of B. Okay, so we have n squared subproblems, and calculating this whole thing, how much time does it take? It takes constant time. It's some number of calculations, some number of if statements and additions and so on. But really, all that doesn't change as the input size increases or decreases. So it takes some constant time. So the running time for this whole thing becomes O to the n squared. Okay, and the space, like we discussed in the edit distance problem, the space could be n squared, O to the n squared, if we have a whole table for every single possible subproblem. If we have a single value for every single possible subproblem, and we store that value, it could be n squared, or it could be O of n if we're space efficient. If we're space efficient, mainly because what we see here, right here, this recurrence only looks at the previous row, or it only looks at the previous column, right? So again, as we stated with the edit distance problem, we only need to store two of the rows, or two of the columns, whatever is smaller, in order to calculate what the longest what the longest common subsequence is. So the longest common subsequence is just the edit distance. So when we do this, I mean, a lot of the steps we took remind you of the edit distance problem, right? It's almost exactly, all the steps we took are almost exactly the edit distance problem. The only difference is, instead of comparing the edit distance, well, it's exactly the edit distance problem. The only difference is that the strings could be anything and not just words, as we were assuming with the edit distance problem. Although even with the edit distance problem, the strings could be anything. So the longest common subsequence problem is pretty much just the edit distance problem, except for the fact that if the characters aren't matching, then the cost is infinite, and if the characters are matching, then the cost is 1. And the price of deletion or insertion of a single character is also 1. So, I mean, well, assuming the price of the deletion or insertion of a character is 1, we could observe the following relationship: that if, as the edit distance grows, the longest common subsequence decreases, but as the longest common subsequence increases, then the edit distance decreases, right? And that makes sense, because if there are more matched characters, the longest common subsequence is just simply a list of all the matched characters between two strings. So if there are more matched characters, then it means the edit distance is smaller. So the length of the longest common subsequence is, what is it? It's n plus m minus the edit distance. Simple as that. Minus the smallest edit distance. Make sense? So the two things are analogous. You'll see both these problems, and the major thing to notice is that the two problems are almost use the same exact thought processes. And in fact, this brings up a larger point about dynamic programming and algorithms in general, which is that a lot of problems are very, very similar. A lot of problems are very similar to problems that have already been solved in nature, and especially with dynamic programming. There are only, I won't say a handful, but there are only a couple dozen good dynamic programming problems that I've seen. Now, there are hundreds of dynamic programming problems written in textbooks and stuff, but really those problems are all many of those problems are effectively reduced to each other the same way longest common subsequence reduces to edit distance. Okay, so with dynamic programming, the key is just to look at a couple core dynamic programming problems in order to master the whole sort of field, at least well enough to get you through those interviews or the basic problems that you might face where dynamic programming might be useful. Okay? All right. So hopefully you learned something. Refer to the labs for more practice with dynamic programming problems, and I will see you in the next lecture. Thanks.